Oxidation numbers. Oxidation numbers are also called oxidation states. This is the charge that an atom in a compound would have if the electron pair in each bond belonged to the more electronegative atom. If we look at the hydrogen chloride molecule, the atoms do not have charges, but they have oxidation numbers. This is not an ionic substance, it's a molecule because it is made up of non-metals. The chlorine has a greater electronegativity compared to hydrogen, so that we treat this molecule as if the shared electron pair will be towards the chlorine side of the molecule and away from the hydrogen side. So the chlorine has an oxidation number of -1, as if it had taken the electron away from the hydrogen atom. The hydrogen will have an oxidation number of +1, as if it is giving its valence electron, which is the one and only electron, to the chlorine. In order to be able to work with redox reactions, you need to know how to work out oxidation numbers. So we have a few rules which you really need to know very well. All elements which are unbonded, not bonded to any other elements, for example, pure oxygen, which is O2, will have an oxidation number of 0. Group 1 elements, which are all of these down here, they will always have an oxidation number of +1. Group 2 elements, which are alkali earth metals, when they are bonded, will always have an oxidation number of +2. Group 7, which are the halogens, will normally have an oxidation number of -1, but they will all be positive if they are bonded to oxygen. I'm going to go to hydrogen now. Hydrogen always has an oxidation state of +1 when it is bonded to non-metals. Its oxidation state will be -1 when it is bonded to metals. So hydrogen with any of these will give hydrogen an oxidation state of -1. Oxygen normally has an oxidation state of -2 unless it is bonded to a more electronegative element like fluorine. Oxygen also has an oxidation state of -1 when it is in the molecule hydrogen peroxide. Fluorine, which is in group 7, has the highest electronegativity. Fluorine is always -1 and zinc is always +2. Now ions are atoms or groups of atoms with a charge. An ion consisting of one atom only, its oxidation number will always be the number of the charge. Then the sum of oxidation numbers for a neutral compound, like the hydrogen chloride molecule that we looked at, the sum of those oxidation numbers will equal 0. And then for our polyatomic ions, the sum of the oxidation numbers for a polyatomic ion will equal the charge on the ion. In the following examples, we have a few molecules and some individual atoms. This, for example, is the diatomic oxygen molecule, the ozone molecule, diatomic bromine. This is how phosphorus normally occurs, sulfur molecule in a group of 8 sulfur atoms in a ring shape, diatomic iodine, and then just the plain neon atom, potassium atom or magnesium atom. All of those have not combined with other elements, so they all have oxidation states or oxidation numbers of 0. We are now going to look at the oxidation states of a few monoatomic ions, which I'm incorporating a few of the rules above. Lithium and sodium are in group 1. They are there. So they have oxidation states of +1 or oxidation numbers of +1. We don't write the 1. Magnesium and calcium are from group 2. So there's our rule for group 2. Their oxidation numbers will be +2. They are also +2 ions. Zinc, as stated in the rule on the right hand side, is always +2 or 2+. Fluorine, group 7, iodine, when they form ions, the fluoride ion and the iodide ion will have oxidation numbers of -1. Aluminium is in group 3, so it is 3+. Now, certain elements can have more than one oxidation number. Copper, for example, can have an oxidation number of 2+ or 1+. Iron can have an oxidation number of 2+ or 3 plus, just like their ions can have different charges. We're going to look at a few compounds in which hydrogen has been bonded to other elements. First of all, in water, hydrogen has an oxidation number of +1. There are 2 hydrogens, so you say 2 times +1. Oxygen is -2, so we are working according to this rule and that rule. The total oxidation number for the entire molecule must equal 0, which is this rule. The sum of oxidation numbers for a neutral compound must equal 0. So as you can see, I've done the algebraic sum of the oxidation numbers in red and they add up to 0. We're going to look at sodium hydride. Sodium is in group 1, so it's always +1. And remember the rule, when hydrogen is bonded to a metal, hydrogen has an oxidation state of -1. It is that rule. This is a compound which gives you a total charge of 0, so the oxidation states must add up to 0. The hydrogen peroxide is also an exception. Hydrogen is +1. There are 2 hydrogens, hence the 2 in front of the +1. Oxygen, there are 2 oxygens, and each oxygen's oxidation number is -1. It is according to this rule. The total charge must equal 0 because the molecule doesn't have, it's a molecule without a charge. And then lastly, if we look at hydrogen chloride or the hydrochloric acid molecule, hydrogen is +1, chlorine is in group 7, it's -1, it's one of your halogens, always -1. And then the total charge, yes, there is no charge, it's a molecule, so the total for the oxidation numbers must equal 0. We are now going to work out the oxidation numbers for sulfur in the sulfate ion and in the sulfite ion. We make an equation with the total charge equaling -2 because the total charge of the polyatomic ion is 2 negative. So there's the -2, which is this -2. Each oxygen has an oxidation number of -2. There are 4 oxygens, so we say 4 times -2. And we don't know what the oxidation state of sulfur is, so I will make that an X and solve X in this equation. When we solve this equation, X turns out to be +6, so the oxidation state of sulfur in the sulfate ion is +6, and each oxygen is -2, according to this rule up here, where oxygen is -2 when it is combined. Now we look at the sulfite ion. The total charge for the sulfite ion is also -2, so my equation must equal -2. I have 3 oxygens in this case, so I say 3 times -2 because each oxygen has an oxidation number of -2, and now we solve for X again. The value for X in the sulfite ion is +4 when we solve the equation. X plus -6 must equal -2, so X equals +4. So the oxidation number for sulfur in the sulfite ion is +4. In the sulfate ion, it was +6. Sulfur is one of the elements that can have more than one oxidation number. Now we're going to look at the oxidation numbers for nitrogen in the nitrate ion. This is the nitrate ion, and in the nitrite ion. Why don't you pause and see if you can solve them yourself? In the nitrate ion, the total charge is -1, so we make it a -1 on the right-hand side of the equal sign. We make the oxidation state for nitrogen X. We have 3 oxygens, so it's +3 times -2. Solve X, you get +5. So the oxidation state for nitrogen in the nitrate ion is +5, and oxygen is in the combined state again, according to that same rule, so oxygen's oxidation number is -2. Please take note, you can say oxidation number or oxidation state. In the nitrite ion, the total charge is -1 again, so I have -1 on the right-hand side. There are 2 oxygen atoms in the polyatomic ion, so I say 2 times -2, that's for the oxygen. Nitrogen is X, there is no rule for nitrogen, so we need to solve it. X is positive 3, so in the nitrite ion, the oxidation number for nitrogen is positive 3. In the nitrate ion, the oxidation number for nitrogen is positive 5, and in the nitrite ion, the oxidation number for nitrogen is positive 3. Next, we are going to figure out the oxidation number for chrome in the dichromate ion and in the chromate ion. Because there are 2 chrome atoms in this polyatomic ion, Cr2O7, the total charge is 2 negative. Because there are 2 chrome atoms, I need to say 2x in this example. There are 7 oxygens, so it's 7 times negative 2, and the total charge is negative 2 again. So let's solve for x. Solving x gives us a value of positive 6. So each chrome atom in the dichromate ion has an oxidation number of positive 6. In the chromate ion, we have 1 chrome, so we only need 1 x. There are 4 oxygens, so it's 4 times negative 2. The total charge is negative 2, so x also ends up being positive 6 for the chromate ion. We're now going to look at a few assorted examples. Here we have a monoatomic ion. It's just a nitride ion, so the charge is 3 negative, so the oxidation number is negative 3. The nitrogen dioxide, each oxygen has an oxidation number of negative 2. There are 2 of them. The total charge is 0, so I have a 0 there, so x is positive 4. In the HOCl molecule, we have a special rule over here where group 7 elements are positive with oxygen. Here's a group 7 element with oxygen. Each hydrogen is positive 1. Oxygen is negative 2. There's only 1 oxygen in this case. So we make the chlorine X. So chlorine's oxidation number ends up being positive 1. The potassium ion will always be plus 1 because it's in group 1. So the oxidation state is positive 1. Magnesium is in group 2. So the ion will be positive 2 or 2 positive. So the oxidation number is positive 2. The sulfuric acid molecule or hydrogen sulfate, if we make the equation, there are 2 hydrogens, each of them are positive 1. We'll make the sulfur X for now, and there are 4 oxygens, so it's 4 times negative 2. The total charge is 0 because there is no charge here. This is not an ion. So we work out X, and it ends up being positive 6. So that is the charge for sulfur in the sulfuric acid molecule. If you look at the sulfate ion on the right-hand side, sulfur also has an oxidation number of positive 6 in the sulfate ion. So this molecule can be seen as 2 hydrogen ions and 2 sulfate ions. So we know that it's a molecule and not ionic though, because they are all nonmetals. In the chlorate ion, we will make the chlorine X for now. There are 3 oxygens, so it's 3 times negative 2. The total charge is negative 1 because the ion has a charge of negative 1. If you solve X, you get chlorine's oxidation number to be positive 5. We do the same thing in the perchlorate ion, except there's an extra oxygen atom, so that is why it is 4 times negative 2. Solve X, and you get chlorine's oxidation number to be positive 7. When you see Roman numerals in brackets, you are actually being given the oxidation number of the element. So for example, iron 2 chloride means that the ion oxidation number is plus 2. We know that chloride is negative 1 because it's in group 7. So if you look at this, you need 2 chlorines to make up iron chloride. So this is ionic, so those are separate ions. So the formula will be FeCl2. If we look at vanadium 5 oxide, we actually say vanadium pentoxide. Pent means 5. So vanadium has an oxidation number of positive 5. Oxygen is negative 2. The formula will be V2O5. Sulfur 4 oxide and sulfur 6 oxide are very different. Sulfur in this compound has an oxidation number of positive 4. In this compound, it has an oxidation number of positive 6. In both cases, oxygen is negative 2. These are molecules, those are ions. Metal, non-metal, metal, non-metal makes them ions. These are non-metals, non-metals, so these are molecules. So the stock notation can be used with metals or with non-metals. We normally see it with metals. To get back to this formula, because sulfur's oxidation number is positive 4, oxygen is negative 2, so we need 2 oxygens to make this neutral. So the formula is SO2. In this one, sulfur is positive 6, oxygen is negative 2, so we need 3 oxygens to make it neutral. These are the formulas for each of these substances.